Hi, welcome to the 6th tutorial in the Python Millionaire Retirement Simulator series. Last time we made a fit to a function of real-world data. We got optimized parameters. We made, if we look here, we made an array of x values that started from minus 0.55, so minus 55% all the way to 75% in 1% increments. We populated a list of y values using our Gauss function that we defined up here, and then we plotted the x values versus the y values, and we quit. So the next thing we want to do is not quit, and in fact we don't need to plot these values at all at the moment. So we can kind of put a pause on the plotting, although I guess it doesn't really hurt to plot them. But what we're going to do now is make what I'm going to define as making a sample distribution. So it's good that we got that plot and all those x and y values for our Gaussian fit to the world market data, or the United States market data. But we want to make something that we can randomly sample from, like we did the real data. And so what we're going to do is make a sample distribution. And so please feel free to follow along. If you don't totally understand everything, that's okay. You can put a comment, ask me to explain something in more detail. I don't know how exactly all that will work, but basically, in a nutshell, what we're going to do is we're going to make a list, and we're going to fill it with we're going to fill it so that the number of entries corresponds to the y value of the x value. So all that is a mouthful, but I'm going to get started here, and hopefully what I do will make some sense. So I'll try to explain everything as I go. We're going to start with making a definition. We're going to call it make sample distribution. And it's going to require some x values and some y values. And you'll notice I didn't use the underscore here, which is my choice, to stick with just x val, y val. Sometimes I like to do that with a definition, just to remind myself that what you put into a definition, it gets this alias inside the definition, but it can be whatever you want to call it outside of the definition. So once the definition is done with it, it doesn't remember it anymore, so to speak. So we're going to start off by defining the maximum of our y value, just saying max y vals. Okay. Next, we're going to define a normalization constant. We're going to call it norm. We're going to say it's 100 divided by y max. That way, our distribution won't be too big or too small, we hope. Then we're going to say y vals is equal to norm times y for y in y vals. Okay. What have we done just there? Now our y values should have a maximum at the value of 100. That's all we did here. We've substituted the former maximum value with a value of 100. Now we want to define a new list. We're going to call it x underscore dist. And it's going to be an empty list to start. Now we're going to do an enumeration, which is the same as a loop, for I, y in enumerate y vals, colon, int y equals int y. Clever, huh? So I'm defining a new variable that I'm calling int y, and it's going to be a forced integer of the y value, because the y value may not be an integer. We'll say if int y is greater than 0, we're going to do the following. We'll now enter another loop and say for j in range int y. That's why we wanted it to be an integer. So we're making a loop over the number of integers. So if the integer was 5, we're now looping 5 times, and we're going to say dot append x vals I. And so what we're doing is saying if the integer was 5, that's the y value that we forced to be an integer, we want to put 5, we want to add to our list 5 times the value of x in that location. And if that doesn't make sense to you, we're going to prove that it actually does force a distribution that looks like the distribution we want to get. And so I think that is the end of it there. And we just need to go all the way back to here and say return x dist. And so we can just double check, okay, x dist is what's being filled in this for loop. And I think we're all set. And so outside of this loop, we want to then make a new value, which we can call x dist. We can call it whatever we want. Equals make sample distribution of x underscore vals, comma, y underscore vals. Okay. So now this x distribution should be just a list of x values, but it's a list of x values that if we plot as a histogram, it should show up fitting, looking just like our Gaussian function. And so earlier we did plot x vals, y vals. Now we're going to do, not quite that, but we're going to do plot.hist x underscore dist. And we're going to say bins equals x underscore vals. So we need to do now a plot.show and assist.exit. So now what we should see is our world data, a fit to the data, and then a final histogram that's very finely binned with these 1% bins that we want to see. And so we'll see if that is in fact what comes up. Okay. Also, I didn't point this out last time, but you can see here that printing the when I asked it to print here, it prints the p optimized and then it prints star p optimized. You can see that what it did is it actually printed the values as an array here without the container. So that's what that did. Okay. All right. So we have this orange. That's the fit to our data. That's centered at 22, as we said earlier. The amplitude of it is at 22. It's centered at 9%. This green histogram is also centered at 9%. It's the same histogram. It's just been renormalized to have a maximum value of 100. And so you can see that it's very smooth. If the other nice thing about using this here is I can zoom in. So we can see that it is in fact a histogram. It's got these, discrete steps. And I don't know how to, if you hit the home button, you should zoom all the way out. Okay. We can't see the original data because this green histogram has been plotted over top of it. I think that if we zoom in real close, no, nothing happens. Okay. So suffice it to say, I hope that the green thing is what we were going for. And I'm going to actually probably cut this tutorial a little bit short by just ending here. So now we have a sample histogram that we've plotted, and based on some logic and reasoning of what we've already done, if we sample from this new green histogram, we have an incredible number of data to sample from. We can get these really discrete steps instead of getting the exact numbers that were provided in the historical data. And so what this would mean that there's 28 instances of the value 19.25 or thereabouts to sample from, so something about minus 19%. So, whatever the probability of that compared to the rest of the sample, it's that discrete value is in there and can be sampled in our distribution. So the point of this particular tutorial was to show how to prepare a list of data to sample from, and now that we have that list, we can sample. So we'll do that in the next tutorial, and I look forward to seeing you there.